we on? Great. Thank you and good morning. Again, my name is Mohammed Gidawi. I'm the PI of this project. I'm happy to be here with you this morning. This project is led by HKUST in a strong partnership with Water Supplies Department, University of Canterbury in New Zealand, University of Perugia in Italy, University of Toronto in Canada, Zhejiang in mainland, PolyU and Chinese U both in Hong Kong, and MIT and Lehigh in the US. You could truly see that the project is multinational and multidisciplinary. We have a strong advisory board from directors of leading government departments in Hong Kong and leading academics. We had a number of meetings with them, and they truly helped us progress the project to get it to completion. The problem we're dealing with is urban water supply system. These are the lifeline of 4 billion people that reside in cities currently. And fortunately, these systems have a lot of problems. They lose about 129 billion cubic meter of water per year. To put that in a context where you might understand, that's equivalent to what would supply 150 cities like Hong Kong. So if we save that water, we could actually supply 150 cities like Hong Kong. Every time you lose water, you got to remember you're losing all the energy that went in to pump that water, to clean that water, to treat it, and all the chemicals and other resources to also get it to the consumers. If you want to think finances, it's estimated the direct costs alone per year is about 40 billion US dollars. That does not include the indirect costs. There is, of course, all other kind of problems that you see: water quality, you see corrosion, you see blockages that occur in the lifetime of these systems. Yet, these systems are large in scale. In Hong Kong alone, we have 8,000 kilometers of pipes. They tend to be buried underground. And from the day we bury them, we can't really get to them. We can't really access them. So when we started, therefore, our objective was to develop a wave-based a new diagnostic system, so we can actually peer into the ground and see these pipes. Waves are all around you. You hear me through waves. Your phone works with waves. You listen to me through waves. Humanity has found, in fact, that waves are one of the best things if you have a system which is not accessible, poorly known, complex. One of the best ways is to transmit a wave into it, receive the echoes, develop wave theories and imaging techniques to see it. And that's precisely what this doctor is doing, is sending a wave, transmitting a wave into the patient, receiving the wave. Of course, theories have been developed and imaging techniques that are inside this computer that allows him, in this case, to see the image. The same analogy is used in ocean acoustics. Here, you could see where the waves being sent into, sound waves being sent to, and they're received, and then they're using all of the theory that has been developed to actually image the fishes in the ocean, to image the sediment. In fact, these days, they're also using it to profile, temperature profile, etc. So the idea was, can we do the same in pipelines? So these pipelines are important, they are costly, they are large in scale, yet our waves are fast. They go at 1 kilometer per second. So that means in 1 second, we could actually get a large sample of echoes coming back. The idea is then, can we develop the wave theory and the imaging to actually turn that into knowledge about the system? And that's really where our project has been in the last 5 years. So the mission was to transmit, to understand these waves and how they propagate in pipeline much better than we have before, then to turn that into diagnostic techniques, new and novel. And of course, we needed to develop the experimental methodologies and labs and field tests to confirm wherever we're. So where are we in all of this? When we started, you start like what you do usually, what you know, and you try to build on what you know. And we did that, I think, for about a year and a half. We were progressing, but frankly, I must admit, we were not progressing at the rate I wanted to achieve all of what we promised to do. So we needed a fresh look. We needed really a paradigm shift. We need to think of these things in a totally different way. So of course, you want to then see what others have been doing in other fields. So it occurred to us, so what are these people doing in ocean imaging, in medical imaging? What are they doing in ocean acoustics? And one of the common things that keeps coming back is the time reversal of waves, which we have not in our field attempted at all. So that was, we had to learn. It became a mission in itself. It was a lots of fun, a bit of divergence for a while, but then we had to prove it. We had to prove it theoretically, we had to prove it experimentally in our system. And we have by now. Our pipes come in different sizes, they come in different materials, and we have to show that it works on all of them. And we have the damping, we have a lot of damping in our system. And damping, what it means is when you do diagnosis, when you do imaging, it blurs your image. So we don't want that. So we found a way to compensate for that damping, and that is now published. When we started, there is not really much work being done on high frequency waves and pipelines. So we had to develop a lot of these theories from scratch, and we have. We tested now whatever we developed here, we tested them both numerically and experimentally. Noise is a killer when you're doing diagnosis, and we now understood, or we have a good understanding, much better than when we started, about noise and noise distribution. It matters what signal you probe with. Not all probing signals are the same, and we've done quite a bit of work on that, and it's been highly beneficial. When we started, even from a mathematical perspective, a lot of the theories had been done in mind for the ocean. The ocean is one connected region. Pipelines are a network. So we had to make things fit to our application, but luckily we have a number of mathematicians with us to help us move forward. We also proved that Bragg resonance is common in pipeline. This gave us a way to look at rather complicated signal and have much more insights into them. Now, with putting all of that, we are able then to come up with a unifying framework for which to image at varying frequency. We have proved in all of our, in the last 5 years, that it is optimal in the sense of signal to noise ratio. It's robust, it's efficient, high resolution, versatile. It's no wonder it is being used in other fields. Okay, so I'll come back, since time reversal is really key. I'll come back and show you a bit about it. Some nice experiments that has been done by others that are visual. But in terms of facilities, let me get you to it. So this is in our lab here in HKUST. This was built all as part of this project. So we have two facilities being built. One is 140 meters long. The other one is about 10 meters long. These are a couple of our guys doing the testing. We also built facilities in University of Perugia through our collaboration, and this is in University of Canterbury in New Zealand. Another signature that really came out with this is the close working relationship with Water Supplies Department. I thank them dearly for all of their support throughout. They gave us this testing site. This is in Beacon Hill in Hong Kong. This is a water supply reservoir. They have some space here. So we talked to them, they gave us the space, and now we build the pipeline around this perimeter. These are some pictures of it. It can be about 250 meters long. We can do networks, we can do branch, we could do all kinds of testing in this facility. Interestingly, our colleagues in water supplies are already using this to train their engineers to detect leaks through listening. So they've been using it. So with the addition we have now, our vision together with water suppliers, we will make this as a center, as a place where smart water technology, all the new development can come in here, can be tested, whether it's ours, whether it's others, whether it's from different places. So hopefully we can develop this in Hong Kong. It's connected to the water supply. Hopefully we can develop it, and we're happy to have this major facility. Wouldn't have happened without the close working relationship with our colleagues in water supplies. They were able to give us 3 testing in the field. So we test in 3 places in Hong Kong. We also have 2 tests that were carried out in Italy, and I'll show you the results of those. But now going back, as I said, one of the new things that really happened here, and we didn't even expect we get there, is this idea of using time reversal. We were not aware of at the time of the application. So when you have a wave, there is a wave source. That wave source could be a stone. You throw a stone on a pond and you get ripples. So these are the type of ripples that all of us, our eyes are used to. And imagine you have a sensor, you could be collecting the pressure at 3 locations or 4 locations here. The principle of time reversal tells you, you take what you measure there, You flip it in time. That means you send last in, first out. You change the chronological order. This becomes your source. And if you make those your source, one intriguing thing about the waves is they refocus back in their sources. They tell you where they come from. They go home. And how sharp, though, do they refocus is actually inversely proportional to to frequency. So that means if you use higher frequency, you get higher resolution, you get more sharpness into it. But of course, for us, high frequency means more damping. So we had to play this to optimize. We build our project around low, high frequency, and I'll show you more of this. But this is really an intriguing. You can find this in the web. It's an experiment that was done in Brazil to show time reversal in something we can see, we can visualize. So they're going to drop a stone here from the ceiling. The stone comes down, it generates ripples. And what they did here is measure the pressure or the water elevation at a couple of places. Okay, so nothing really earth-shattering about that. We all would expect, you see, there's a stone, there are ripples. So the intriguing part is now what they're going to do is they're going to take whatever they measured, they're going to flip it in time, and that becomes the source. And just bear with me because the end result is really worth it. It's cool. So now these become the sources, what they measured. Okay, we're going to speed through this video, right, to gain a bit of time. We will slow it down when it's doing what it should do, what waves like to do when you send them back. So observe what happens. Okay, the wave refocuses back. You see the water splashing where the stone used to be. So it actually tells us where did the stone go. So what it means to us, or what it meant to us, seeing things like this, is that if I'm standing here and measuring, and let's say you plunge in a pool or you threw something in a pool, I don't need to know where you are. I could measure and send back and find you and find the source of those. To us, already signs are coming saying, but leaks are sources, pipe junctions are sources, pumps are sources. So maybe we could just turn all of this. We could time reverse these waves and they will tell us. So that was really the initial thing about us starting to look at this. Then we looked, because that was gravity waves, acoustic waves. So we looked at what people were doing in the ocean acoustics. And this is an experiment, I believe it was done in the Mediterranean Ocean. They send a wave from here to about 10 or 15 kilometers away. And what they send is a short blip. They send a short compact source sometimes. So we'll hear in the video blip. See, very short sound. You will hear what they're going to receive. Now, what they're going to receive about 10 kilometers away. A very elongated signal, what we call echoes. You know that when you speak in tunnels and all that, you get that echoes. Why there are echoes? Because waves go directly, but also waves zigzag up and down to get there. So there is a spread, what's called dispersion. Now, this is very nice to us because this could be thought of the pipeline. This is our water. These are the walls of the pipe. And we have these, as I will show you later. Now, notice what happens when they're going to time reverse this. Okay. So they took what they measured here, they time reversed it. Now they're going to send it back in the ocean. And you see, you get the compact source. So the source refocuses again, collapses into a short period at 10 kilometers away. What it means again here, if there was a whale, if there is a whale here singing, and I'm measuring elsewhere, I don't need to know where that whale is. I could just measure what I get, reverse it, and it would locate. So these are great things at locating sources, and that's what we are after in this project. So we've done this with many, of course, experiments, but I'll just show you one. Here's in the pipeline at Beacon Hill. We send again a short burst. We measure at the other location. You see, we get the echoes. We get that signal spread in time. So now we time reverse it, send it back, and we get the refocusing exactly at the location, but we get these side lobes. Anybody in the audience who worked on this or as a scientist will know these are the artifact of the fact that you don't measure at every point, or you don't measure long enough. So these are what we call a side lobe. In fact, maybe you didn't pay attention, but we've seen already the side lobes. This is the focus. We know where the stone here, but you still have some ripples. So if you want to get rid of these in these experiments, you measure at many more points and you do it and you will see only the stone and everything will be quiet. What it means, if we want to get rid of this in practice, we need to measure at more places, but our system is not accessible. So we have to deal with these side lobes. So now that we proved time reversal for us, let's see how we test it. And we're going to split this into low frequency, high frequency. Why low frequency? We send low frequency waves because they have long range. We can test kilometers of pipes in a few seconds. That will tell us, though, low frequency has low resolution. That means we can only tell defects within tens to hundreds of meters. The idea then, once we are close to where defects are, we go in and hit it with the high frequency, and we will be able to precisely determine, well, precisely, and now we're getting to a few centimeters, to the order of centimeters. So let's see how we work with low frequency time reversal. This is a test that we've done in the field in Hong Kong, in Gao Tau Kok. I think this was about 700 meters long. Send a wave, receive. Please notice we only need to collect about 0.6 second of the sample. This is, by the way, all automated now. Get the data, it all goes to the computer. The time reversal is around, gives you the image like we're trying to emulate like what that doctor was doing with a patient. And this is when this is our patient, is our pipeline. So we want to see what is inside it. We see things that are already there. We see connections and so on, and those all show up in the time reversal, but we see new things. We saw a hydrant line that was not on our maps. So we contacted our colleagues in water supplies and they confirmed that indeed there was a line there, but it was not on our maps. Well, they had a pressure reducing valve. We knew they did, but they told us it was out of commission. In one of the tests, we believe our results were telling us it's working, something is happening. So we contacted them and indeed they confirmed that it was back online. So the point I'm trying to make here is this is not a leak finder. It's actually a way to map the whole system. It's a way to find things, junctions and so on that you didn't know. It's a way to tell you about whether your devices are working or not working. It's a way to determine new defects. Right? So we tested this also in Yulong in a 1.5 or 2 kilometers pipeline. Again, send the signal, receive, do the process and get the image. And the image there, we suspect that there are 2 leaks. We are talking to our colleagues in our supply department to confirm it. Of course, we need to dig. To dig, we need to get permits. This is a major highway, so we need to get, and we haven't done that, but that's where we are suspecting that there are 2 leaks. They suspect there are leaks as well. We got data. This is from Trento in Italy. Our colleagues collected that. They sent it to us. We applied our methodology. We detected there is a leak and an air pocket. In this case, it was actually verified in the field. This is actually this data predates our project. It was done in Milan over 5 kilometer, actually about 10 kilometer distance. But we want to see the range. So again, we tested it and you see we get the double peaks. These double peaks is an implication that we have multiple defects. And in fact, when they dug in Milan, they found a number of leaks bunched up together. This is another interesting one. When we were just early on the project, the water supplies was collecting real data in Hong Kong, in North Point in Hong Kong, and they were seeing each day at 4 o'clock a drop in pressure. And the question is, what causes it? That means the question is really, what is the source of this? So once we got these ideas of time reversal, we said, let's play. If we have something like that, what will happen? So now we just play it backwards. Okay, we do the time reversal and we'll watch where it refocuses, right? And you see, this is where it refocuses. So to us, it tells us that's where the source must be. And then we need to check. And in fact, in checking with them, it was confirmed. So this is where we would predict. It was confirmed that indeed there is a government truck, another government truck that comes around 4, fills up the water. So every time it fills up, there is a drop. So again, here, this is not a leak finder. It's finding somebody who is tampering with your water and so on, where it could be used. But again, the limitation here is that with low frequency, you can only tell to within tens of meters. It's costly to dig within tens of meters. So we want to get closer. We want to get to the order of a fraction of a meter, hopefully. And that's where high frequency is. So we tested it, and this is the test we've done. We wanted to see how closely we can detect this opening, and it can be of the order of centimeter. Interestingly, we also detect this support here. So that means we can separate two defects that are even within this distance, right? That's what this resolution allows you to do. The other important though in practice is these supports, whenever pipes have these supports, they're gonna wear off with time. So if we do this test and we see changes in this peak, it tells us that there are some problems about to occur. So it's better to find these problems before they occur. We wanted also to see if we can find junctions with these high frequency waves. Can we actually localize the junction? And we do. But this is, again, from a practical point of view, it's very important because a lot of the leaks are actually occur at junctions of pipes. And when pipes get older, these junctions start to be loose. If we apply this time reversal, we'll see changes here, and that will tell us that these junctions start to move. We can fix the problem before it becomes very large and we have leaks and sinkholes. Problems also occur inside, as you saw in the earlier picture. You may have noticed there is corrosion. So we want to see, can we localize things that are as small as a magnet here, which we did. We also asked our colleagues in water supply, they gave us lining from a pipe. So we put it here and we can find it again to the order of centimeters. So this is a way of telling us in the future that we don't need to wait for the pipe to crack to say, oh, something has happened in it. We should be able to hopefully see problems when they start to occur, when these linings start to peel off. So through the work we've done in the last 5 years, we have 8 test beds that we developed. We have 1 patent filed and 3 in progress. We have been working very closely with the water supplies department, as you already seen evidence for it. We have labs together. We are testing in the field together. In fact, we got a project recently from drainage service department because they have 200 kilometers of pipes that are also pumped. So we've been trying to apply some of this knowledge there. We developed fundamental knowledge that is encapsulated in 80 journal papers, 30 conference papers, and 30 theses and reports. We trained 27 PhD students, 18 postdocs, 20 FYPs, 5 high school students spent some time with us, and 10 MSc students. These students are postdocs. Some of them are here, but they are now everywhere in the world, right, making their own impact. We are also happy that the last time the monitoring team of RGC visited us, this is the picture during the visit, they think that we're doing exemplary work. They see that we're doing real world impact. They can see the interdisciplinary nature and the new techniques we're developing. They really like our facilities, and we do. And again, thanks to the collaboration with our colleagues in Italy and New Zealand and with our water supplies department, of course. And we're glad they think we're doing an excellent job. At least that makes us, the hard work pays off. With all of these development, with all of the theories, the labs we have, the human capacity that we develop, we really are poised now to save water and energy. Remember, just to summarize, we are losing about the equivalent of what would supply Hong Kong, 130 times Hong Kong. We're losing direct costs about $50 billion around the world. So surely, if we can do better than this, yes, we will increase the wealth of the cities. Yes, we will reduce interruption. We will improve sustainability, strengthen security, resist climate change, reinforce resilience, and enhance urban health. And that's what we truly want. The only little price you pay is I had more white hairs, more black hair when I started. I have now more pounds on and more wrinkles, but that's a worth price to pay, I think, for what we've done. Thank you very much.
Okay, thank you. I'm Tong Chuan Che, the moderator of the Q&A session. Here we have a few questions. Professor Gidavi, question 1. When will this technology be implemented in Hong Kong? And if it is possible, what is needed to apply the technology in practice?
Yeah, thank you, a very excellent question. The technology one of the problems we have, and we already had, and we still have, is accessibility in water supply system. And with system where we can find access, we are ready to test it, and then we are trying to build access. But we're already actually working with our university. Our university is building a pipeline, and we want to go in there and build access. So my advice here to whomever is expanding is don't bury your pipeline. It's not, you want to work on smart cities. The move is to have smart cities, make your systems accessible to new technology. The way we still in practice do, unfortunately, lots of water infrastructure is buried underground because the past was to forget about it as long as it's doing its job. But if we want to save water, save energy, make it accessible to us, to our technology, to other technologies. So that's actually one of the difficulties. So one of the difficulty you see that with the high frequency, we could not yet test into the field, at least not on Hong Kong, because the only way we access this system is through fire hydrant. Fire hydrant is okay to do it with low frequency, but with high, we actually need to send these transducer into the pipeline. So some access, so really let's work on the access. It's not gonna be the technology by itself, it has to get in. Essentially, the doctor has to see the patient. If we can't see the patient, but our thing was, so maybe if I scroll back, this is the problem where I must say historically in civil engineers, because maybe we had more pressing issue, we didn't think of this. But let me get you back to, how do I, okay, sorry, bear with me, I'm gonna get there quick, trying. Okay, so this is what we don't have in civil engineering systems. We don't really have a way to transmit and receive in lots of these places. So we build this, we're dying, but luckily again in our university, and we're being also talking to a water supplies department, in Hong Kong, they're doing the new development, which is the Anderson Road development, which is kind of to showcase all the new technologies. We're hoping we will build the access, and we talk to them, and there is an agreement that we will build access and we'll be implementing it there.
Thank you, Professor Gedavi. Here is the question 2 from Peter. During the receive of the source and the time reversal signals, there may be some background noise, and how to clean this noise, and what is the area of the noise added to the real location of the source?
Yeah, when we did the work with our colleagues actually in electrical led that work, and what they found is with flowing water, which luckily we have, in flowing water, the distribution of the noise tends to be Gaussian. And with a Gaussian distribution, these time reversal are actually optimal. Optimal in the sense they maximize signal to noise. So we tested it. We are now at the level where we can get it almost, what was the number? I think it's of signal to noise ratio. I think it's about 10. So as long as we have a signal to noise ratio about 10, we're actually, it's working so far. Of course, we want to push boundaries more, but that's where things are now.
Thank you, Professor Gedavi. I think we have 2 minutes for one last question.
Good.
Do you have any plan for the future next step work?
Well, yeah, as I said, we actually already started. We already started with the university, and hopefully we will. What our vision is we want to show water supply departments around the world what happens if you combine the technology with access. And we are building part in our new campus. We're building actually, we will be building a water supply system where we can integrate this within it. So the problem is integration of this technology. And hopefully by showing these to different communities, then they can start to rethink their future designs, of allowing access. The other things we've been also looking at, how do you do higher resolution? How can you actually tell things even to a higher resolution? We already started research on that. One of the things that we found recently, which is exciting, do you really need to send the signal? Because there is a lot of signals already there, and we are trying to tap on the background signal, because we find that there are signals up to 20 kilohertz. So there is really, this opened up to us a lot of theoretical and practical issues that we're hoping to address in the next 5 years and so
on. Thank you, Professor Gedavi. I think due to the time problem, we should end this session now. Thank you.